All right, today we're doing something really cool. We're going to crack open the blueprint for one of the most important robots in modern manufacturing. We're taking a super complex technical manual and turning it into a simple, clear guide. We're going to show you exactly how you could design and, yeah, even build a high-precision robot arm right on your own desk.
So, think about the smartphone in your pocket or the laptop you're using. You ever just stop and wonder how they get put together? With that kind of pinpoint accuracy, thousands and thousands of times a day. It seems almost impossibly fast, right? Well, it's not magic. It is some seriously clever engineering, and there's a very specific kind of robot at the heart of it all.
And this is it. Meet the SCARA robot. Now, it might not look like the flashy robots you see in sci-fi movies, but this thing is the real workhorse of the entire electronics industry. And today, we're going to unpack exactly what makes it tick. And, get this, how you could actually build one yourself.
So, first things first, what is a SCARA robot, really? Well, the name itself actually gives us a massive clue about what it's designed for and why it's so incredibly good at its job. Okay, SCARA stands for Selective Compliance Assembly Robot Arm. Whoa, that's a mouthful, right? But its superpower is hidden right there in those first two words, selective compliance. So what does that mean? It means the arm is unbelievably rigid up and down. It won't bend when pushing something in, but it's got just a little bit of give or flexibility side to side. And that is the secret sauce for assembly. It lets the arm easily guide parts into place without getting jammed up. So here's the main takeaway. A SCARA robot is the undisputed champion of moving things quickly and precisely across a flat surface. Just picture a robotic arm that can absolutely zip across a tabletop, picking up tiny little components and placing them perfectly, over and over and over again. That is the SCARA's world. And how does it do it? Well, just look at its design next to a big, complex six-axis robot. See, a six-axis arm is kind of like our arm. It's flexible in every direction. But the SCARA? It's intentionally simpler. Its two main joints rotate in parallel, which makes it super stiff in the up and down direction. It's a deliberate trade-off. It gives up the ability to twist and turn like a human arm in exchange for pure, unshakable stability. And for high-speed assembly, that's exactly what you need. All right, so now that we know what it is, let's build one, right here from the ground up. We're going to start with the robot's anatomy, its physical body and skeleton, before we get into the brains of the operation. Every great robot starts with a solid foundation. So step one, we begin with a heavy, stable base. Can't have it wobbling around. On top of that, we mount the first rotating joint. That's the shoulder, which is connected to the upper arm. Then comes that second key joint, the elbow, which connects to the forearm. And see, that shoulder-elbow combo is what gives the robot its incredible horizontal reach. Finally, we add the vertical Z-axis for all the up and down motion, a little rotating joint for the tool, and of course the end effector. That's the gripper or whatever tool's actually doing the work.
But a mechanical frame is just a skeleton. It's cool, but it can't do anything on its own. To bring it to life, we need muscles and a nervous system. And in our case, that means the electrical components that provide the power and carry the commands. So let's check out the parts that give this robot its spark.
Now, here's what's really amazing about this. Look at how accessible these parts are. We're talking about NEMA 17 stepper motors. Yep, the same kind you find in pretty much any hobbyist 3D printer. Then you need some motor drivers like the A4988, which basically act as translators between the brain and the motors. And for the brain itself, we can start with something as common as an Arduino or an ESP32 microcontroller. This isn't some unobtainable sci-fi tech. It's hobbyist-level electronics powering a legit, professional-grade concept. Okay, so we've built the body, we've wired up the nervous system. Now it's time for the most important part, the brain. This is all the software that translates a simple command, like pick up that screw, into a series of perfectly timed, synchronized movements. So the way this robot thinks is structured in a 4-layer chain of command. It all starts at the very top, with what we call the mission planning layer. This is where you give the robot its goal. Think of it like you're the boss saying, okay, robot, your mission is to pick up the chip at coordinate XY and place it over at coordinate AB. Simple as that. Once the robot has its mission, the second layer immediately kicks in, motion planning and kinematics. This is the robot's brilliant inner navigator. It takes the where, those target coordinates you gave it, and figures out the how. It calculates the smoothest, fastest path to get there. And most importantly, it figures out the exact angles that the shoulder and elbow joints need to be at to reach that specific spot. Next up, layer 3, the control loop. This thing is a tireless supervisor, and I mean tireless. It's operating hundreds, sometimes even thousands of times every single second. It is constantly checking the robot's actual position against the path that was planned. And it's making tiny, real-time corrections to make sure every single movement is perfectly synchronized and incredibly precise. And finally, we get to the hardware abstraction layer. This is the final translator. This is where the rubber meets the road. It takes all those digital commands from the control loop, commands like move joint 1 by 0.01 degrees, and turns them into the specific electrical pulses that the motor drivers can actually understand. This is where thought becomes physical action. And this is a peek behind the curtain at the core of the robot's intelligence. This equation is part of something called inverse kinematics. Now, don't worry about solving it. The point is, this is the mathematical magic that lets the robot take a simple set of coordinates, an x and a y, and instantly calculate the two specific angles its joints need to form to get there. This right here, this is the heart of the robot's brain. So we get the theory, right? We've seen the mechanics, we've walked through the software, but how would you actually go about building this thing? Well, the key is not to try and eat the whole elephant at once. Let's look at a clear, phased blueprint for how to actually do it. You see, a project like this only feels manageable when you break it into chunks. You'd start small. For the first couple of weeks, you'd just focus on getting a single joint to move exactly where you want it. That's it. Then, you'd add the second arm and start implementing that inverse kinematics math to master moving in 2D. From there, you build up, adding the z-axis, adding the gripper, and only after you've mastered all the fundamentals, then you move on to the really fancy stuff like adding a camera for vision. It's a ladder. You just take it one step at a time. So as we wrap up here, let's just quickly summarize why this specific robot design is such a powerful and honestly a really smart project for anyone who wants to dive deep into robotics.
Building a SCARA arm has some huge advantages for learning. First, the complexity grows with you. You build it piece by piece, so you're never totally overwhelmed. And you're learning the exact same principles that are used in real, multi-million-dollar industrial robots, but you're doing it on a scale that fits on your desk. The math is also in that perfect sweet spot. It's challenging enough to be really meaningful, but it's way, way simpler than a 6-axis arm. And maybe most importantly, every single skill you pick up is directly relevant to a huge part of modern industry.
So there you have it, the complete blueprint, from the base plate all the way up to the control logic. We've just demystified the unsung hero of the assembly line. So the only real question left is, now that you have the blueprint, what would you have it build?